Okay, so I'm going to talk today about sort of a case study and how we work with our sort of customers to sort of co-develop products, and that's quite easy for us to talk about because it's the way our business works today. So this is the outline of the presentation. Talk a little bit about Sivers Photonics. Maybe not everybody in this room might be aware of what we do and the markets that we participate in. Talk about our manufacturing platform. So we have a 100mm wafer fab up in Glasgow. Again, we're going to talk about AI. I wonder how many talks are going to cover AI today, but it is, of course, very important, a very exciting opportunity for many of us in this room. And primarily the products that we manufacture that are going into the sort of the next generation of AI architectures, and finish off with a quick summary. So just a quick background about who Sivers Photonics are. So we regard ourselves as the world's most advanced supplier of custom 3.5 photonic devices. So we're based up in the outskirts of Glasgow in Blantyre, where we do both design and manufacturing in the same facility. We're not a startup company. We're pretty well established. We've been going for more than 20 years. So we have a 4-inch wafer fab with a capacity of about 5,000 wafer starts per year. We process about 1,000 wafers per year because most of the activity that we do today is very much sort of NRE based. So lots of opportunity to really expand. And really what we offer to our customers is a complete end-to-end chip solution. And this is where we get into the sort of co-development model. So what we have is customers coming to us with a chip specification. They don't know how to design the chip, they don't know how to fabricate the chip, and we can do all of that for them. So that's the way our business operates today. So up in Blantyre, we have 80 members of staff, including, say, 10 guys who are designing the chips, everybody else, mucking in and fabricating the wafers and so on. So we actually supply known good die on tape to our customers, so we're offering a complete end-to-end solution. And today, we are a sort of key supplier to many Fortune 100 customers and Silicon Valley startups. So we export about 92% of what we manufacture up in Glasgow. Pretty much all of that goes into California. So if you think of the 6 biggest tech companies in the US today, we've got commercial interaction with 5 of those 6 companies today, which is pretty amazing when you think we're just a tiny company in the outskirts of Glasgow. Okay. Let me just take a minute to talk about the sort of the broader wafer fab picture of what's happening north of the border. So today we've got 5 operational wafer fabs up in Scotland, stretching right across the central belt. So over in Greenock, we've still got Diodes operating, and that's by far the biggest wafer fab up in Scotland. We then have ourselves in Blantyre doing compound semi-photonics. Over to Livingston, we've got Broadex doing 8-inch silicon flame hydrolysis PLCs for optically passive devices. And then over on the East Coast in Fife, we've got Semifab doing sort of custom foundry and MEMS, and we've also got Classic doing silicon carbide processing. So we don't have the same scale of industry as we had 20 years ago, but we still have a very sort of strong fab industry, and we still try and punch above our weight. And I think we do that because the fabs that have survived are the ones that are focused on the more sort of niche semiconductor areas in the industry, maybe diodes aside. And some of the opportunities that these companies have are really exciting. We're all sort of involved in areas that are really going to grow in the future, so tremendous opportunities for us. I would say, however, it's very difficult running a fab in the UK. I mean, let's be blunt. We are facing sort of international competition from companies who are heavily subsidised, really heavily subsidised, and we just don't have that level of subsidy right now. And that may not change in the short term. Who knows how things might develop. So it's a very challenging sort of economic situation that we find ourselves in, and we have to be agile. We have to find the right sort of technology areas that we can actually win. We have to understand where we have a competitive advantage and where we can actually compete. We cannot compete against Asian suppliers, of course. So we have to find the right sort of niche of markets, applications where we've got some competitive edge. So it's a very challenging environment, and I would have to take this opportunity to say the UK fabs, it's not just a Scottish fab issue. This is all the fabs in the UK need more support. And we will lobby and continue to lobby as heavily as we possibly can to bring in support into the wafer fabs if we want to retain that capability going forward. Okay, so we supply devices into a really broad range of markets. The 2 big ones for us are datacomms and sensing. So datacomms is driven by the components going into the data centers, which is heavily now focused on sort of AI architectures. We also make devices that go into sort of biometric applications. So if you take one of these things, for example, it's a sensor. It's got lasers at the front. It's got lasers at the back already. But all it does is really sort of distance detection. In 10 years' time, this thing will be able to do a lot of scary things, okay? It's not just a phone. This is a sensor, and we'll carry around these sensors in our pockets. So, very exciting opportunity for our technology. And then the final sensing application is LiDAR, for autonomous vehicles of the future. But really, data comms driven by the AI rollout is probably the biggest opportunity that we have as a business. A bit more details about what we really do up in Blantyre. So we've got very strong design expertise, a team of 10 guys designing sort of laser chips. We've got a very sort of strong history, library of existing designs. Pretty much everything we do today is sort of NRE and prototyping. That's a tough game to be in because you can't scale it. You can't really make a lot of money in it, and you don't really fully utilize your fab capacity. So we have to get into volume production, but we have the capability to do complete end-to-end fabrication of everything inside the facility, including reliability, qualification, and so on. The only thing we outsource is base epi, which we outsource to our colleagues at IQ in South Wales. So technology expertise, we historically have made a very, very broad range of devices, laser chips, modulators, detectors, optical amplifiers, but our main focus moving forward is very much DFB lasers for the applications I've already mentioned. We are a key player in the whole silicon photonics ecosystem, and I'll talk a bit more of that in a couple of slides. So we have our sort of advanced 4-inch indium phosphide platform where we have sort of all of our commercial users based on. And we are a very much established volume supplier in the market. We have somewhere around 50 million devices out in the field. Most of that would be in Asia, in the sort of PON market space. But we have a lot of inherent capacity to ship devices from our fab today. So just a quick slide on the indium phosphide product platform that we have. We don't have a PDK, so for customers to work with us, they have to go and talk to our engineers, our design team. So it's a bit of a clunky process, but it works, and that's the way that we sort of co-develop, devices and systems for our customers. And really on these sort of 4-inch wafers, we can, produce a very broad range of device types. We're typically making very, very small chips, so some of the products we have in excess of 100,000 die sites per wafer. We designed the platform to give us high yield, high reliability. High reliability is a really important aspect, particularly for AI networks. You cannot have a laser failing after 28 days in an AI system because you go back to T0 to restart the process. So reliability is one of the main sort of factors within how parts and components are selected for these AI networks. And we designed the process to be scalable to high volume. So yes, we're not there just now, but that's very much the plan to take the fab up into high volume. And a lot of the sort of architecture is really designed for silicon photonic flip chip die attach. And these are some of the nice images that we get, some of the nice sort of process technology that we have within the fab. So we have an interesting mix of, let's say, geometry scale within our fab. In some senses, we're doing sort of 1980s technology in the fab. We're processing 2-micron features because the feature size doesn't shrink because it's determined by the wavelength of the laser, which never changes. The only exception to that is the gratings. So we have sort of 100 nanometer feature grating. So we've got lithography at 100 nanometers, and we've got lithography at 2 microns, and we've got nothing between those 2 points. So it's quite a unique situation that we have. But some of the key features that we have on here, we have etch facets. So typically when you make a laser, you break the wafer up into bars, and during that break process, you create the optical facets. So we do that on wafer. We etch the facets on wafer. That allows us to put the optical coatings onto the facet at a wafer level. So that's a way to improve the reliability and improve the manufacturability and cost of the products. We have a very strong partnership with IMEC. I think we have an IMEC representation here today, but we've been working with the photonics team in IMEC for about 5 years now. And what we're doing there is optimizing this silicon photonic hybrid flip chip attach. Everybody's heard of silicon photonics. It's an important market. It's growing rapidly. And basically what we're adding here is a sort of 3.5 component. So on a silicon wafer, you can do a huge amount of photonic functionality. You can do routing, muxing, demuxing, modulation, detection, but you can't create light. And that's why you still need the 3.5 laser to create and illuminate this photonic circuit with light. And one of the approaches that many of our commercial customers are taking is to basically take our red laser diodes in a gel pack and then flip chip them down onto a sort of 8-inch or 12-inch silicon wafer. So that is now starting to become a sort of mature process that's been deployed in industry. That can only be done if you have the very high accuracy die placement tools that are produced by companies such as Micra, for example. So they are placing these chips passively. Passively means you don't switch the laser on to couple into the waveguide, with deep submicron placement accuracy. Without that technology, this whole process doesn't work. This whole architecture doesn't work. So this is something that we've been one of the sort of pioneers in developing this with IMEC, and it's created a huge amount of commercial interest on the back of this. And we have some certain features in our devices that really facilitate that process. We can put gold tin down onto our chips, which people like because you don't have to put gold tin on a silicon wafer. We have backside fiducial marks as well. And we're typically supplying these devices in array format for flip chipping. So a very nice capability. And these devices are bonded into pretty much all of the main silicon photonic platforms today, whether that's come from GF, Tower, VTT, even TSMC are getting into this space as well. So again, there's a lot of opportunities for this type of technology moving forward. So let's talk a wee bit about photonics and AI networks. Now, we've had an excellent use case of AI and what it's actually doing for industry, society, and everybody knows this. And I'm in no way an expert on AI networks, but let me try and talk to you about what I do know about it. If you think about NVIDIA, what NVIDIA are doing today and the networks that they're building, they've got the Blackwell chips, they've got the Grace chips, and how they're all interconnected. 90% of that connectivity is copper. Copper works. It's pretty clunky. It's dirt cheap to install. It's very expensive to operate because of the power consumption requirements. And that is the big issue that we have with copper. What we're going to see over the next sort of 3, 4, 5 years is a gradual deployment of optical AI. So this is basically the GPUs, the CPUs talking to each other through an optical interconnect right down at the sort of board level and within the racks in the data centers. This has to happen to allow these clusters to sort of increase in performance and increase in size. And we're at a very good position in terms of how to use our technology, our laser technology, to really sort of drive this change, I would say, in how the sort of networks are actually constructed today. So we get improved latency. Latency is really important because it speeds up the sort of the processing time, the learning times of the networks. In many cases, the GPUs are sitting idle for 30% of the time waiting for data to come in because the copper's not fast enough. More power efficiency. So that's the electrical power that it just takes to drive the signals down these copper cables, which limits also the size that you can actually create the networks. Cost reduction, less power, less cost. And there's been a huge investment already in this sort of ecosystem to drive this sort of transition over to optical interconnects. So this is what we have today. This is what a sort of NVIDIA system today. It's a rack. You see Jensen try to pick it up, he can barely lift it. Sort of water cooled. I don't know what that thing costs. That probably thing costs like $500,000 for all the components inside that. So it's quite clunky, but it works. Everything in there is connected electrically. There's no optics within that. There are optics within the sort of systems, top of rack, talking to different racks, etc. But it's very much dominated by copper. You're limited in terms of the size of the network that you can actually roll out because of the copper transmission distance limitation. So moving to optical breaks all these barriers. Okay, so we go all optical, bandwidth of 8 terabits per second. We have a customer that I'm just going to talk about. It's actually demonstrated 16 terabits per second. That's important. The other important factor is bandwidth density. Getting data off a chip in terms of shoreline density is also very important. And this allows these networks to be increased in size up to potentially 100,000 GPUs that we'll see over the next few years. And the cost saving, the energy it takes to move one bit from one GPU to the next is going to drop from 50 picojoules to 5 picojoules. So that's where the data centers will become much, much more power efficient than they currently are today, as they're consuming so much of the energy production today. So this is the specific case study. So we've been working with a company called AR Labs. They're a Silicon Valley startup, well-funded, developing very sort of disruptive optical I/O architectures. So what do they actually do? So if you look at the image here, imagine this big black square is a Blackwell GPU, for example. It could be a CPU, it could be an XPU, it could be a FPGA. It's some very sort of, you know, data-hungry, expensive ASIC. So what AR Labs are basically doing, they're taking these sort of 4 teraflops CMOS optical chiplets and placing them right beside the ASIC. So this is what people call co-packaged optics. So these are basically silicon photonic chips. They manufacture these up in Global Foundries, Fab 8 or Fab 10, up in New York, where they've got the high-speed electronics. They've also got integrated Mach-Zehnder ring resonator modulators to modulate the laser light that comes from our power source and convert the electrical signal into an optical signal. So you can imagine this would become a box, a module of this size. There's no RF coming out of that box. There's no high-speed electrical connection coming out of that box. It's all coming out on a fiber array. So basically, the whole sort of thinking around this is you convert from the electrical domain into the optical domain as fast and as close as you possibly can. So you're not sending RF signals over any significant distance at all. And this is a very sort of disruptive approach. So this is all great, but it needs an optical power source. And this is where Siever's laser technology is being adopted. So we basically supply the laser chip here, which goes into the sort of remote laser module. So even though it's called co-package optics, you know, we've got the optics right in beside the ASIC, the laser doesn't have to be there. The laser could be a kilometre away in a nice cold environment. Our lasers don't like it when it's hot. You know, this thing's running super hot, maybe 110 degrees C. So it makes a lot of sense to have the laser remote where you can control the temperature. And if it breaks, our lasers don't break, of course, but if it ever did break, then you can quickly replace it. You can unplug it, throw it in the bin, and reconnect a fresh laser. So many reasons to do that. That's probably a $50,000 module. You know, a Blackwell chip is like $20,000, $30,000. So what they don't want is parts failing within this module that's going to take down a Blackwell chip. Okay, so that's why you do stuff remotely if you possibly can. Optics is good because you can transmit down an optical fiber with effectively no loss over a few kilometers. So really, we've worked with our customer to really work on the specifications. You know, what's the best way to design that chip, manufacture that chip, to get it into the market. So there's a lot of sort of discussions that take place. So this all sounds fantastic. What's the issue with this? Cost. The issue is cost, right? I've already said copper. NVIDIA turn up at the photonics shows and they like to scare the photonics industry. And they say, well, we get our copper cables for free of charge, basically. They just cost nothing. You know, you've got to produce your optics for something down in that range. And everybody gets scared by that. And this is the big challenge for the photonics industry as a whole. You know, the supply chain is not there to do stuff at the right volume, at the right cost. So what does that really mean? So that means making this laser module. AR Labs probably want to sell that for $500. We're going to sell them a chip for $50. NVIDIA probably want to buy the whole thing for $20. So there's a massive discrepancy in terms of what the optics industry can actually supply today with, you know, the price point that actually makes it completely compelling for NVIDIA to design their architectures around this technology. So there's still a lot of challenges for the photonics industry, but still a very exciting opportunity and something that has to work in the future. If you think about the architectures we have today, I did mention there are some optics within these networks. That's a mixture of active optical cable, which is very basic VCSEL technology, or 800G pluggables. The 800G pluggables are too inefficient, they're too expensive, they cost about $1,200 each for a little box this size, and it just can't fix the problems that the networks have today. So exciting opportunities for us. This is about a financial slide. I don't like talking about this, but the opportunity is incredibly big. You know, as we see deployment, you know, as the sort of penetration of this technology, you know, really gets into the data centers, then we have an incredibly big opportunity in this space, one that would outgrow the fab that we have up in Glasgow within 12 months. So, you know, we don't have an obvious solution of how to go beyond that, but it's a good problem to have. Then I think I've just got a few final sort of technical slides about the performance of the devices. These are the type of devices that we sell. So this chip is about 2 millimeters by 1 millimeter. So on a 4-inch wafer, we get about 3,000 die sites. You know, we are looking to yield maybe 50% to start with, and we're going to sell it for up to maybe $50. So, you know, we could be generating in excess of $50,000 revenue per wafer from our fab. So that's why it's such an exciting opportunity for us. And this is the performance of the devices that we get. So 70 milliwatts of optical output per laser, coming out of a very, very small spot, so it can be coupled into the silicon photonics very accurately. And we produce these on a very sort of tight grid around a sort of MSA specification, of which we're one of the sort of founding members. And then we also make 16x arrays. So what you see here is the deployment of you know, a 16x laser array that is then sort of muxed into sort of 16 fibers. So you have 256 carrier signals. So it's a highly parallel architecture, and then you can put a 64 gigabit signal onto each of those 256 carriers to get 16 terabits of bandwidth. So a very, very sort of exciting deployment. But we have to remain competitive. You know, the only reason that we are selling this stuff with, you know, into some of these startup companies is because, you know, we continue to sort of, you know, develop the technology. You can see here, you know, hitting all these individual challenges start to become quite difficult. You know, everything is in the channel, but a few of the lasers are quite at the edge. So one of the things that we've now started to do is introduce tunability into our laser devices. That's going to allow you to make much more dense grids, and really allow you to sort of scale up the number of lasers within an array. So again, that's another important sort of differentiator that we have from our competition. So today we only have 1 or 2 other competing companies in this space. They're both US-based companies, one of which is Lumentum, and one of which is McKee, and, you know, they don't offer this yet. So it's important, you know, for, you know, the small companies like ourselves to be as agile as possible, trying to identify the opportunities where we can still be technically competitive, and it's the only thing that really makes us survive. Okay, and this is my last slide. So just a quick summary. So we've got complete in-house design for design and manufacturing up in our Blantyre facility. Our IMP platform provides the most advanced custom DFB laser array products for next-gen optical I/O applications going into AI networks, and we've got very, very strong traction with the sort of leading industry partners in the AI industry, right up to the guy at the top. So it's a very exciting time for us. Thank you.